First, I'm going to show you how you can install the software developed in this paper named ShapeGen3D. So this is the paper. If you go down, you will find a link. If you click on it, it will send you to a GitHub folder. There you can download the raw file, which is a MATLAB app file. You can take the file and paste it into any directory. Here I have pasted into a directory of the MATLAB. So from the MATLAB, you can double click on it and you can install it just by clicking on it. And after installing, you will find it in your app section here. So if you click on it again, the app will open and you can start using it immediately. Formulating hexahedron element is extremely straightforward. First, you need to select the option, the hexahedron or brick element, and this will show multiple sub-options to build the element. For example, this is polynomial degree along x, which is the degree along the x-axis. This is for the y-axis, and this is for the z-axis. You also have the option to choose either the Lagrangian or serendipity family elements. So if you click on it, the formulation would be for Lagrangian element. If unclicked, it will formulate serendipity element. And finally, you can choose the integration quadrature. There are two options, Gauss-Legendre and Gauss-Lobato. So you can choose any of those two. So as an example, I will generate a very common element, which is a 20-node brick element. And this is used widely by commercial software such as Abacus. So to do that, I choose the polynomial degree along x as 2, 2, 2. And as that's the serendipity family element, I don't click on the Lagrangian family. And after choosing all the options, I hit the generate shape functions. And the software will determine the shape function, integration quadrature, and the graphics for this element. So the formulation is done, and this is the 20-node brick element. We have already created a 20-node brick element, and now I'm going to show you how to build a 21-node brick element that we have built on the paper. So the 21-node brick element doesn't fall within the realm of standard elements, so we assign it as an arbitrary or custom element. So we click on that and several options appear. So if I click on one, it shows that two tables. So one table is for the nodal coordinates, which is the left tables, and the right tables is the monomial basis functions. So we can input all the nodes and monomial basis function for the 20-node brick element, but to make our life easy, we can just import the element that we have created previously. So we click on this import element and it will be populated automatically. So as you can see, there are 20 nodes, so it's 20. The 21 node has an extra node, so we click on 21 and another column appears, which is 0, 0, 0. So we can assign it the value as 0, 0, 1, and we can hit check, and the software will plot the elements, and we can see that there is a node at the top of this surface. And now we have to manipulate the monomial basis function for the added node. So in the paper, we have followed this formulation. So this monomial basis function vanishes when z equal to -1. So basically, if we reach the bottom surface, this x square y square would be 0. So after inputting this function, we can hit generate shape functions, and the software will formulate the element. So the element formulation is done, and we can see the 21st node shape function, which looks like this. Here I present an example of high order elements. So for this case, the polynomial degree along x is 4, along y is 4, and along z is 2. So I take the bar there and I hit the Lagrangian family to make it a Lagrangian family element, and I choose the integration quadrature as Gauss-Lobato, and I hit the generate shape functions to formulate the element. So from this graphics, you can see that there are 5 nodes along x and y and 3 nodes along z. We have implemented a lot of graphics options to allow you to check element properties, such as the interpolation, inter-element compatibility condition, and local support conditions of the element. So the graphics options are presented here and below. I will go each one by one. So this is the nodes. So by clicking on that, you can activate and deactivate the nodes, which is the black dots. This option activates the node numbers, show you the node numbers. It's straightforward. This one is for the integration points. So as we have used Gauss-Lobato nodes with Lagrangian family, the integration points overlap on each other. So that's why all the black dots, which are nodes, are colored as red. This is the weights of the integration points. We have also implemented surface integration points. So those are marked as green, you can see here. And finally, the surface integration points includes the parametric coordinates. So here the green one is basically the unit vector that is perpendicular to the surface of that integration point, and red or blue are the x and y at the local coordinate or in the parametric coordinate. And finally, if you want to check interpolation and local support condition, you may choose the fill as 0. That will make all the values of 0 shape functions as blank and show you only the value of shape functions that is non-zero. You can increase the fill, which will increase the resolution. For this example, it is obvious that the shape function is 1 here, non-zero at the surface that contains this node, and 0 at the surface that do not contain this node. So this shape function of this element satisfy the interpolation and local support conditions. And you can check this condition for all other shape functions. After you formulate the element, you need to export the data such as shape functions, node coordinates, integration points to implement in the finite element models. To make it possible, we have created this block, which is the save data. So you can click the options here. For example, I've clicked the build function file and I click the save data. So this option will create a text file. That text file will contain all the information of the element. And if you click the build function file, there would be another MATLAB function file that you can directly use for finite element implementation if you use MATLAB. So to show you an example, this is the results created as a text file. It contains the interpolation function, the nodal coordinates x, y, z. It contains all the shape functions. So there are 75 shape functions. It contains all the 75 of them. It contains the integration points and weights, which is the W. And that is for the text file. You can also choose the function file, which contains all the information, including the integration points for region and surface integration. So it includes nodes, integration points, weights, shape functions derivatives evaluated at the integration points. You have the nodes on the surface, you have the integration points on the surface, you have the integration point weight on the surface, your shape functions evaluated at the integration points on the surface, and these are shape functions derivatives, and this is the parametric coordinates for the integration points of the surface. So by calling this function, you can import all the information that's written in this function file. I will finish this video by generating a random element that doesn't fall within a standard element library to show the full overview of the software. So I'll go to arbitrary or custom element, and I'm going to formulate a pyramid element using monomial basis functions as the interpolation functions. So I input the nodal coordinates as I like. By hitting check, I see that the given nodal coordinates is able to formulate a geometry that looks like it. And then I'm going to input the interpolation function. I can go one by one, but to make my life easy, I can hit the autofill, and the software will fill up the interpolation function by itself. And I can choose to change the order. For example, I can make x square y square, which doesn't obviously work because along y-axis there are just two nodes, so there's no way I can replicate on y square. So hitting on that, this should give me an error which is rank 4 out of 5. That means one of the monomial basis function is not correct. So I can make it x square y, and still it's not working. Hence I'll go with x square. And now it is able to formulate the element with these monomial basis functions. I can check the shape functions by increasing the pills, and you can see the shape functions looks like this, which is shape function number 1. And these are all other shape functions. This is how it looks like. So that would be all. Thanks for watching.